after finding my x value of my point of intersection, I'll go ahead and set up my final definite integral and then math 9. So we'll go ahead and integrate, right? We're going to integrate from alpha a up until what? Well, x equals 1. Top curve, that would be ln of x, close input plus 3, minus bottom curve, that would be 1 over x. Close integrand with respect to x, and math 9 it. So on my calculator, we'll just math 9 it, and we'll do our definite integral. The integral from, I didn't do alpha a on my home screen, so I want to go ahead and store alpha a. What did we say? 0.45291. Store alpha a, math 9, alpha a to 1 of, and I put it in my function, my top curve was a natural log, by 1, minus bars, y bars, function y2, bless you, closed quantity with respect to x. Voila! I'm getting about 0.661. Is that what you guys are getting? 0.661? Yay! Math works. So we're getting about, and make sure that you don't lose your answer point after doing all your calculus right. So 0.661 would be correct in 3 places. Awesome. What questions do you have about your area? Area, let's look here. Find the volume of the solid that results when the region R is rotated about the line y equals -2. And so I've gone ahead and added y2 there, right? This black line, y equals -2, and so our origin is over here. Right, here's our origin. So you can see that that black horizontal line is y equals -2. That's going to be my axis of rotation. So we're going to go ahead and spin that original region R about my axis of rotation, y equals -2, and consider the solid that results, right? If we consider the solid that results, we can see the outer radius given by a big green and the inner radius given by the black would show up in my final, right, in my final cross-section. So if I consider the shape of a cross-section, what's this going to look like? Oh gosh, it's going to look like about here, about here. You guys see it? What's it going to be? Thwack! I know you guys were waiting for me to say that for a long time. Ta-da! There's our washer cross section with outer radius big R in green, and my inner radius little r in black. And I know the volume V of my solid will result from integrating from A to B my area function A of x of a typical cross section with respect to x across my x values from which the cross sections can be taken. So what do we do for this case? Well, we already have that intersection point, right? Thank goodness, we've already stored that as alpha A. So we'll go ahead and integrate from alpha A to 1. And now we're going to go ahead and do the formula for our cross section. Our cross section, A, is a washer whose area is given by pi r squared minus pi r squared, where r is my outer radius that's larger and r is my inner radius here in black that's smaller. So my area function A of x is going to be A of x equals pi. What's my outer radius? Oh gosh. How are we going to keep that positive? How are we going to keep my outer radius positive? Well, we need to do top curve minus bottom curve. My top curve is the natural log curve, the ln of x. Yes? So we'll do top curve is y equals ln of x, close input, plus 3, minus bottom curve. What's my bottom curve? My bottom curve is y equals, right? Isn't that y equals -2? So y equals -2. Notice the use of the parentheses. Top curve minus bottom curve. Both of them are solved for y. They should have x's in them, right? How come this doesn't have x's in it? Because it's a horizontal line. This quantity is my green big R. There's my green big R. So I still need squared. Minus my inner radius. That's the black radius. How do I get the black radius? My black radius is top curve minus bottom curve. What's my top curve? My top curve is the red function, right? What was that? Y equals 1 over x. Did everybody see it? So 1 over x minus bottom curve. What's my bottom curve? Solve for y? -2. Now that I've delineated my a of x function by rewriting my area formula for a cross-sectional area of a washer, I'll integrate my a of x function across my range of possible slices and get the overall volume. So here we go. I know that my integral from 1 to a of x with respect to x is given by, pardon, here we go. We want math 9, and do I want to put the pi out front? Maybe I want to put the pi out front and do pi r squared minus pi r squared. I'm going to do that. I'm going to go second insert pi, and on the inside I'm going to do r quantity squared minus r quantity squared, close integrand, and then dx. So here we go, alpha a up until 1. Here's my big R quantity squared. I need parentheses. So here's my parentheses. Ln of x plus 3 was my top curve. Bars, y bars, function, y1. Minus a -2 is plus 2. Close big R squared. Minus inner radius, little r, given by top curve, y equals 1 over x. That was my bars. Uh-oh. Any parentheses? Hey! Minus bottom curve, close, squared. Can we do it? Pinch of salt over the shoulder. Did you guys do it yet? Did you guys do it? Ready? 16.719. Raise your hand if you got that. All right, 16.719. Yay! Math works. That's pretty sweet. So there's our 719. Awesome. Okay. So this washer was nice because our outer radius and inner radius were both kept positive by doing top curve minus bottom curve, and my axis of rotation was beneath my original region R. Let's go ahead and take a look at a different set. New region and boundary curves. Ladies and gentlemen, consider the region R in the second quadrant, bounded by the curves y equals -x over 2. So we know that must be my blue curve here. Y equals 5 must be my red. X equals -1 must be the vertical. Can we find the area of R with respect to X versus with respect to Y? Absolutely. So let's go ahead and shade my original region. Two separate integrals to be the same. We know that my area of this region is just given by the integral of my rectangle heights, right? Times my rectangle width, infinitely thin dx over the course of the region from where rectangles can be drawn. So I'll go ahead and draw my typical rectangle. With respect to x would be a vertical rectangle, shown in blue. I need to find this intersection point right here. And this intersection point is just given as x equals -1. So let's go ahead and in our graphing calculator again. clear out our y equals menu. New functions for your enjoyment. Second e to the in my angle I want opposite of x over 2. Happy fingers. 5. And I want to get a new window. How about -4 to 0.25? And -0.25 to 6. Second, calculate, intersect. 5, first curve, enter. Second curve, enter. Guess. Voila! Looks like -3.218876. (218876). Now we can set up my definite integral from a to -1 of top curve is what? Y equals 5 minus bottom curve was e to the negative x over 2. We can write that, right? We should write that, e to the negative x over 2. If I define it as y1, I could write it as y1 as a time saver. I don't know if it's better. It might be safer to write e to the negative x over 2. In any case, I'm ready for my decimal approximation. I'm going to math 9 on the home screen, comma, baby. And I'm going to go from alpha. Oh, I didn't store that new one, did I? I better store the new one. -3.218876.
And you can just restore from there.
I can just store from here, Brandon?
Yep.
Store alpha A. Thank you, sir. Here we go. Math 9, math 9, math 9. Alpha A to -1. Top curve was y equals 5 minus bottom curve was e to the negative x over 2. With respect to x, raise your hand if you got 4.392. Anybody get there already? Hey, that's good news. Okay, so we should get exactly the same thing. What are we doing with respect to y? So why are we doing it 2 different ways? To make sure we're comfortable, right? Integrating with respect to x or with respect to y when it's easier to integrate with respect to y. So let's verify that we get the same thing now. But let's go after a different plan of attack. 392 is what we want to be correct. Awesome. Okay, with respect to y, how are we going to do that? Well, now we're not integrating, right, from left to right, scanning the region from left to right, and keeping my rectangle heights positive by doing top curve minus bottom curve. Now we're going to go ahead and integrate from bottom to top. And our rectangle heights are now going to be kept positive by doing right curve minus left curve, solve for x. So I have y's in it. We're going to scan now from, right, we're going to scan from bottom to top. So how in the world am I going to figure out this? Right? How am I going to figure out this y coordinate? Well, that happens when x, Brandon?
Would we just calculate with the same second Calc 5 that we did the first point with?
We could if I had a y equals for my second curve, but right now this is an x equals. But that's okay. We can evaluate my first curve, y equals e to the negative x over 2, at x equals 1, and just get my corresponding y value. So this is just y of -1. So we can go ahead and put a -1 there, and we should get e to the positive 1/2. So isn't this e to the 1/2? We can verify with the trace, and just trace and y curve at -1. And we get 1.648723. And we can verify that that is e to the, what did I say, 1/2? And that's 1.648723. I'm going to store this in alpha b now. Now I'm going to integrate. Now I'm going to integrate from lowest y value. That's alpha b. The highest y value, what's that? 5. Right curve minus left curve. Right curve solved for x is what? X equals -1 minus left curve. Left curve solved for x is, oh crikey, I've got to solve this for x. No problem. I can solve this for x by taking the natural log of both sides to bring down that variable expression out of the exponent and get on the ground floor where I can deal with it. So I'm going to rearrange this formula, y equals blah 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 with x's, to be x equals blah 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 with y's. Brendan?
I'm doing it in my head.
Yep.
So it would be x equals the negative natural log of, the negative natural log of y over 2.
I'm with you, except I think it's 2. I think it's -2 ln y. Is that right? So I take the natural log of both sides. That gets rid of the e to the and gets my exponent on the ground floor. I'll now multiply over by a negative and a 2, and now I get my x alone. Is everybody good? Awesome. Thank you. Thank you, Brandon. Let's do it. So I get -2 ln y, close, dy. I don't have a y variable to integrate on my calculator, right, the same way, but I'll just math 9 it and just use x and pretend that x is that. We should get the same exact thing, right? So here we go. Math 9. Lower limit, alpha b. 2 upper limit, 5. Right curve solved for x is x equals -1. Minus. Left curve solved for x is minus, so I'm going to just go plus, don't tell anyone, plus 2 ln y. Oh gosh, oh Jiminy crickets! 4.392. Hey, math works. Again. Or is that still? Does math still work? Riley, or does it work again? Still works. Okay. What kinds of questions do you have so far? So we've done area, we've done volume, we've done with respect to x, we did a little area with respect to y. So what's complicated about it? Well, we can now start spinning things around axes of rotation, right? Where my original region is below my axis of rotation, and see how that affects it. So we're good with our Math 9. That means from now on we'll probably spend less time doing our Math 9 evals and focus more on the setup so we can make sure we get you to some trickier ones. So here we go. Find the volume of the solid results when the region R is rotated about the line y equals 7. So we already have our region, we have it entered, and we're going to spin it where? We're going to spin it about the line y equals 7, right? Where's that? Oh goodness. So 1, 2, 3, 4, 5, 6, 7 is right here. If we spin this region about the line y equals 7 and consider the solid results, thwack. We'll go ahead and take a slice perpendicular to my axis of rotation and turn it out to face us. And what shape will it be? It'll be a washer. Whose outer radius is shown in green and whose inner radius is shown in blue, and whose area formula is still our friend pi r squared minus pi r squared, where r is my outer radius in green and R is my inner radius in blue. You guys ready? Can we do it? Awesome, let's go to it. So my volume V is given by the integral pi times the integral from leftmost x value. The leftmost x value we already found. That was leftmost x value wasn't that alpha A? Alpha A? Up until rightmost x value of my solid would be x equals -1. My outer radius, right, squared, is going to be big R squared. Big R is the green vertical line segment. How do I keep a vertical line segment positive? By doing top curve minus bottom curve. Everybody, let's focus in on the green line segment. Outer radius big R. Top curve is y equals 7. Minus bottom curve is y equals isn't that e to the negative x over 2? Close big R squared minus little r squared. What's my little radius? That's blue. Blue is kept positive. That vertical line segment is kept positive by doing top curve solve for y minus bottom curve solve for y. What's the top curve solve for y? Y equals 7. Minus bottom curve solve for y. Y equals
5.
Which is just 2 quantity squared. But I'm writing like this so we can see close integrand with respect to x. Oh, can't wait. Math 9. Alpha A. 2, -1. Oh, I need a pi. We need a pi in front. Second insert. Don't forget that. That'd be bad news bears. Left paren. 7 minus y1. Close big R squared minus, and isn't that just 2 squared? We can do 2 squared or we can do 4. That looks like R squared minus R squared, so I'm going to do that. Woo! And what's that? What's that right there? Did I not do a pi? What's that? What's that business? Did not do it? Do you guys know what happened? I erased it?
No, did you not press the second key?
I don't know. Maybe. I want to see if I get with you guys though.
Error.
Oh, you put
Go to
pi
the
in an
y
exponent.
equals menu.
Oh, pi and an
You didn't hit
exponent?
the second key, so you just raised it.
So can I just overwrite it? No, now it's still up in there. Ah. Raise your hand if you got the same thing. Oh, that's great. Woohoo! I'm feeling okay now because we took an axis of rotation that was above our region. We still kept our radii positive and produced a positive volume overall, so we know we're on to something here. Okay, what questions do you have so far? I thought there were some hard ones here. None of these are hard. These are all easy, right? What's going on? What happens if we find the volume of the solid results when the region are on the same region rotated about the line x equals -1, right? X equals -1. So now we do our first volume, right? Our first volume where our axis of rotation is a vertical axis of rotation. So let's draw our turn arrow. We're going to spin our original region around that axis of rotation. And consider the solid results. It looks like we've got no problem. Thwack. If we turn this out to face us, what shape do we have? We just have a circle, so this isn't even a washer. But I will need to keep my radius positive. Right? I will need to keep my radius positive. So in this case, to keep that radius positive, which is a horizontal line segment, right? I'll do right minus left to keep that radius positive. You guys see that? So I always want to connect, right, my radius from my boundary of the curve to the axis of rotation. And I'll keep that horizontal quantity positive by doing right curve minus left curve, regardless of which quadrant I lie. Right here I am over in quadrant 2 where x values are negative, but I'll still keep this positive quantity. So let's write our area. Our area formula is a equals pi r squared. And my radius is little r in red. So for us, my area function, we don't want a of x, we want a of y because we're integrating our stack of coins in Gringotts Bank, right? We're integrating from bottom to top our vertical stack of coins, not integrating left to right. So here we go. Pi r squared. R is kept positive, little r in red, by doing right curve solve for x. X equals what? -1 minus left curve solve for x. We already decided was not -2 ln y. Is that right? All right, let's write our calculus. We got to do our calculus still. Bottom y value is b. Can we store that? Topmost y value is 5 pi r squared. And my r was that. I don't have to write it all again. But looks like I already started. Math 9. Oh, did I do it again? No exponent today. No, sirree. Alpha b. 5. Oh boy. I want r squared, so I need a paren and -1 plus 2 ln y close squared integrand y. Take a deep breath. Hail Mary for the end zone. Janice goes up. 22.147. Did anyone else get that? Yes, you guys got it? Yes. So sweet. Sammy, I'm still not finding anything hard. I mean, are there any hard ones here? You guys are killing it, right? These are easy cheesy, right? So what makes it more difficult? Can we do one that involves sine of x, cosine of x, area? You guys can do that, no problem. And rotate about y equals -1. That one is going to be good. And rotate about line x equals 2. Awesome. Okay. So go ahead and do this with your partner. I'm going to pause the recording, and I've already done this, and we'll share our answers. So I'm going to pause the recording, do this with your partner, make sure you get it. Okay, ladies and gentlemen, and so as a result of your checking and practicing with your partner, we should have gotten about 7.472. Box that. Let's go ahead and do a similar, now that we solved our stored in alpha A and alpha B. Let's go ahead and do a similar one, but now, again, let's make sure that we're able to go around an axis of rotation that is above my region. Here we are in quadrant 4, right, where my y-coordinates are negative, and yet we can still ensure a positive result here, so long as we keep in mind our top curve minus bottom curve to keep those radii positive versus negative. So let's go ahead and do our volume question if you haven't already. Our volume question. And I'll pause the recording again here. Okay, as you continue to check with your partner, we want to make sure you're comfortable writing the area formula for a typical cross-section. In this case, again, washer results in a pi r squared minus pi r squared. the key is how do we keep these radii positive? So we're going to go ahead and do our red outer radius, our green inner radius, little r, and we'll write our formula. So here we go. Our volume V will be given by pi integral from A to B of outer radius r in green will be kept positive. How? By doing top curve, solve for y. That's y equals what? -1 minus bottom curve, solve for y. Wait, isn't my red radius the outer radius? My bottom curve, solve for y. That's my parabola. That was which one? That was y2? Yes? y2? Minus inner radius squared inner radius is green, kept positive by doing y equals top curve, solve for y equals -1, minus bottom curve is my blue sinusoid, that's y1, right? y1. Can we do it? Check it, don't wreck it. All right, here we go. We'll try it, we'll see. Oh, I need a pi again. How many times have I done that? Every time? That's all right, you go ahead and say it. Every time. You've done it every time, Mr. Fritz. All right. It's fine, it's fine. Not bashful. A to B, parentheses for my outer radius, because I have to square it. -1 minus y2. Bars, y bars. Function, y2. Close r, squared, minus, open little r. Inside little r, -1. Minus, bars, y bars. Function, y1. Close little r, square little r. With respect to, how many syntax errors did I make in that little expression? No? We'll see. See if it agrees with Hayden 194. Raise your hand if you got that. Anybody else get that? You guys did. Oh, that's great. You guys remember having an emulator. That's pretty touchy, right? Lag. Take one step. Back, Mr. Fritz. Okay, one to go, guys, and it's going to work out perfectly. So our final one, here we go, our final one. Guys, I saved the best for last. What? I saved the best for last because now we're going to go ahead and do with respect to y with a hole in it. So this is the big bad mother daddy of them all. If you can do this, then you should be good to go. Brandon.
We don't have that much grading. Oh, it's in the middle. I thought we didn't have another orange.
Oh, it's back in the middle? Okay, yeah, sorry about that. So I must have said, oh, we don't have enough time, this is too difficult. In a previous year, before students can handle it, and now you guys are obviously rock styling to the top. So let's go back to the middle and let's see if we can do this. So find the volume of the solid results when the region R is rotated about the line x equals 2. And we're back to these curves. So we already had some values, and of course I overwrote them. So let's try and visualize this, you guys. We're going to spin around x equals 2. So everybody find our axis of rotation. Turn it around. Wow. Black. outer radius, inner radius, so our outer radius is red, our inner radius is black, and we're going to keep our area formula positive by doing right curve solve for x minus left curve solve for x in each case, even though my axis of rotation, right, is to the right of my region here. So we'll keep that, no problem. Is that right? 2 minus a negative 2 on y. Is that what we got when we saw that for x? Yes, yes. Good. That is r in red, big R, squared. And my little radius was in black, and that is kept positive by doing right curve solve for x equals 2 minus left curve solve for x. What was left curve? Negative 1. Good job. Pi r squared minus pi r squared sets up our volume integral. In the interest of time, I'm going to integrate from lowest most y value already found was e to the 1/2, e to the 1/2. Up to the highest most y value was y equals 5, was that right? All right, guys, I know we can do this. And we're right on time. Oh my gosh, that never happens. Here we go. Pi r squared minus pi r squared. So last time of the day, James, it's never too late. Pi first. Math 9. Math 9. Math 9. Lower limit, e to the 1/2. Upper limit, 5. R squared, open big R, 2 plus 2 ln y, close angle input, close big R, squared, minus, open little r, 2 minus a negative 1 is, 2 plus a positive 1 is 3, squared, don't need to close, already closed, party on, excellent. Did anybody get 104.931? For the final time today, math works. That's great news. You guys are awesome. I hope you enjoyed this rip-roaring area and volume review. By looking at area and volume before we start AP test prep, that's going to take care of at least one pre-response question for the rest of the year. So way to go. Good work. You can pack up and visit quietly. I'll stop the recording and post it on our Moodle. In the next class, I'll try to start with example 1.